So, yeah, so the subject is the interesting topic for me at least. It is was started by a professor at the University of Rochester in USA. That university worked on confinement of magnetic plasma in for a fusion reactor. Eventually, if they ever achieved to confine it, and they had the idea of pulsating the magnetic field for the confinement. And so they said, okay, why not? We should try also on the aluminum reduction cell. And we published a few papers on this subject, and I decided to continue on my own with Valdis' help because they are essentially looking for whatever funding or something to continue on their side. So I will first discuss about the mobile model. That is something that I've developed with them, well, at least with the student, the PhD student that is now a professor at the university, Ibrahim Mohammed, that he has developed this mobile with me, and I'm using it for trying to map the stability. So because we have two parameters, we have the frequency of the oscillation and the amplitude. So that's a 2D space. And if I try to investigate this 2D space with MHD Valdis, I would need weeks and months and to build a map. So I'm trying first to investigate that with this mobile model that I will present. And then I will go to using MHD Valdis to study the compensation, dynamic compensation of the cell. That it's essentially oscillating the current in the compensation bus bar to oscillate the magnetic field in the cell, that oscillate the force field, that oscillate the interface in a different frequency. That is the frequency of the wave, to try to have an anti-resonance effect. That is what I'm explaining here. So essentially you create a fluctuation that is not helping the natural wave to grow and helping this to stabilize the cell this way. Okay, so I'm going to use MHD Valdis in the second part, so I'm introducing it here. So MHD Valdis, as my previous presentation, it is a software that is designed to study stability. So you compute the current. Okay, I can go over this way. You compute the electrical network. You get the current density. You compute the magnetic field. You need to consider the magnetization of the pot shell. Then you have the Lorentz force that give you the flow in the interface deformation steady state. And then you activate the dynamic mode, and you get either the damping of the wave or the amplification of the wave if it's unstable condition. Okay, then this mechanical model was initially invented by Peter Davidson, that is a professor at in UK and Cambridge University, and he developed the idea of having a pendulum with a plate that represents the metal pad, and then cryolite that is essentially imaginary because it's no friction, but it is the electrical resistivity of cryolite. And if you bend the plate, or if the pendulum moves, it's creating a force. Now, this idea is very imaginative, and it was used to explain what is the dynamics of a cell stability. But we try to improve on it because it's not predicting the same stability as a cell of the same size. So now we have developed, Ibrahim and I, a pendulum model, mechanical model, with friction. So instead of having the pivot on the top of the ceiling, it is now a pivot on the surface of the plate here. So it requires less energy to move, And also to even make it even easier to move, we have a parameter that is the position of the center of gravity of that, in principle, aluminum plate with a uniform density, but not anymore in that model. The density is imaginary changing over the thickness, so that we have a center of gravity that is getting closer and closer to the pivot point. So that means if you move the center of gravity exactly at the pivot point, you need no energy to move. So that's how we can calibrate this model to behave more like a real cell. That's all the physics there. The mathematics is all there. So you have two equations, because a displacement on one side will create a force on the other side due to the Lorentz force. And so you start with any shape, any position, and it will oscillate between the two, according to those two equations on top. And what's important about those equations, it is this parameter A contains current density, current magnetic field, and the ACD, it's H0, and big H, capital H, is the thickness of the metal paddle, or the plate in that case. And then the friction up here, in that equation up here, that if you tilt it and there's no Lorentz force, so there's no current density, it will stabilize quickly because of that friction. And then you can do the linear stability analysis on that system, and you get that equation down here. And you solve for that equation, and the solution is of this is a complex number. The real part is the frequency, and the imaginary part is the damping. Like exactly what Louis explained in the morning. Before lunch. So it's easy to solve it. So it's so quickly, so simple. And now after that, the next thing is, okay, I will skip this one. And the calibration, what is done, so you calibrate the two parameter, the position of the center of gravity and the friction, and you can reproduce this. So this column here, whoops, that's a mistake. Okay, so this column here is the MHD Valdez result for the stability, the damping rate of the wave. And this is a calibration that I presented already. This is a new calibration. And now I'm perfectly reproducing two values, but then on average I'm very close to reproducing all the data produced by MHD Valdez. And for this column of number, I need a week of computer time. And to get the equivalent on the plate model, it's a fraction of a second each time you ask for, and you use this apps that is here. You say solve, and then poof, you have the answer. So you can generate data very quickly. Okay, so then after that, this is a new test for the model, the mechanical model, the mobile model, is that you improve the magnetic field, and you also want to see the model is predicting an improvement of stability. So here I'm improving the magnetic field by having compensation loop in this cell that is the 3-met cell in Hamburg. And so I'm improving it by passing 20 kiloamps in the two compensation bus bar at both ends of the cell. That is improving a lot the magnetic field. And this is the prediction of MHD Valdez for this improvement of magnetic field. So you have this side here, it's predicting critical stability at 4.3 centimeter ECD. And this side here, it's predicting a very fast damping, so a very stable cell. And that's the number that you want to reproduce in this case is the rate of damping of the wave, that is 0.021/second. So to get this in the mobile model, I need to decrease my magnetic field from 30 Gauss to 22.7 Gauss. So it's not an absolute comparison because it's a constant magnetic field, and in the real cell it's a distribution of magnetic field, but it is quite realistic. So that's why we are I like very much this kind of simple model for investigating, like in that case, the map, the stability map of my dynamic stability compensation. Okay, so the next point is that if you remember the parameter A, there's J0 and multiplied by BZ. So if you compensate one by the other, like I'm doing here, so if I'm increasing J0 by 20%, and at the same time I'm decreasing BZ by 20%, I'm predicting the same stability in this mobile model. That is not the point of the paper, but that's interesting to highlight. Okay, so now I want to investigate the map. So I need to raise a point that this plate is not oscillating at the same frequency as an interface wave between the two liquid. This plate is a natural frequency for the size of the cell is 0.07 Hertz, and we'll see later that the natural frequency of the wave in the cell is 0.02 something. So now I will quote frequency in terms of in relation to the natural frequency. So it will be 1x for the same frequency, or 2x if it's double the frequency, etc. So I will present result for those. So this is without any compensation, dynamic compensation. So the critical stability at 4.3 centimeter ACD, a 1x oscillation. That means at 1x the frequency, the same frequency of the natural frequency of the plate oscillation, and the amplitude is also 1x. That means that the same amplitude as the J0. So going from 0.5 J0 to 1.5 J0. That is a quite big change of current. You imagine in a real smelter, you'll be, let's say you operate at 300 kiloamps, you will go from 150 to 450 every like a fraction of a second. So it's a bit crazy idea. But that was that's the only way I can do in that plate model. So I'm studying first this way. Okay. So the next is, okay, I try 1.5, I try 2, 2.5, and I'm getting the best value is 0.01542 Hertz. That is 1.99x for the frequency compared to natural frequency. I'm getting, with that kind of compensation, I can reduce the ACD from 4.3 to 3.855 in that mobile model and keep the critical stability. So it's working quite well in that little model. Okay, next. So here I'm showing the result, 1.99. So this is the damping for those conditions. Okay, now I'm done with the plate, the mobile. I'm shifting back to MHD Valdez. I'm trying to use that information that I gained to quickly try interesting case to analyze it with MHD Valdez. And I will not do it the same way, because it's not a practical way to oscillate the full pot line. But you can do it by oscillating the current in the compensation loop. That is way more practical. It has the same effect. Here I'm raising the point that the static compensation is better at 30 kiloamps, because I'm getting an even bigger damping. And so I will be my base for my static compensation. And on top of it, I will have a dynamic compensation. Okay, so I will study 2x, 3x, 4x for the frequency. Right now at 10 kiloamps amplitude. No, not 10. Yes, 10. So it will go from 25 to 35 kiloamps in the compensation bus bar. So I'm showing here. So 10 10 kiloamps amplitude, so it means that my compensation, the current in my compensation bus bar goes from 25 to 35, and that oscillates the magnetic field in the cell, and that oscillation then will generate a fluctuation of the interface at the given frequency that I'm exciting. So 2x the natural frequency up to 4x. And the result is that here we have a result at 3x. So you see the spike here on so this is the frequency I'm exciting, and this is the natural frequency of the wave. So it is damping, and after that I have what's left here is the oscillation that I'm forcing. So the damping is better than you will achieve without doing this kind of compensation. So this is 3x. It's not the best. The best is 2x. But now I will present first 4x. 4x is too fast. The metal is not following. You see the leftover here, this little fluctuation is due to the 4x excitation, but the interface is not following this excitation. So 4x is too fast, and 3x is less efficient than 2x. So what I've discovered from the mobile model, and then now I'm getting confirmation with MHD Valdez, the best anti-resonating frequency is twice the natural frequency of the wave. Now after that, the question, what is the amplitude? That is the best. So the next question is, I tried double the amplitude to 20. So I will, instead of going from 25 to 35 in my compensation bus bar, I'm going from 20 to 40. And I'm getting a result that is, with this increased amplitude, I'm getting a worse result than with the 10 kiloamps amplitude. This is in contradiction with the mobile model, but my explanation is the mobile was studying a fluctuation of the current density, so the line current, and it's when you go lower, you stabilize your cell. When you go higher, you destabilize. But on average, the fluctuation improves the stability. Here, I'm oscillating the compensation loop, but the optimum position is 30 kiloamps. And so I go 20 is not as good. I go 40 is not as good. It's overcompensation. The other one is undercompensation. So the result of this is that the too big amplitude is not improving the stability. It is decreasing it. Now, I have no clue yet, because I have not investigated outside of those two numbers what is the optimum amplitude, and I don't even have a value of the perfect frequency, because I only try 2x and not 1.99, and I don't know if it's 1.99 or 1.98 or something. But the issue is that every time I try something, I have to wait overnight to get the solution with MHD Valdez. So here it is the solution for the 2x 10 kiloamps amplitude. That is the best number I've got, the best damping I got. And a 20x is not as good. Okay, so I'm getting to the conclusion. So using the static compensation, I'm getting from a critical stability without compensation at 4.3 centimeter ACD. With 30 kiloamps static compensation, I can reduce ACD to 3.1 to get back to critical stability. But with the dynamic compensation added to that, I can reduce to 2.9, and I'm still stable, on the stable side. And I stopped there my R&D, so I cannot give you the number that is the final number, because I have not found the optimum frequency, I have not found the optimum amplitude, and I have not reached the limit of stability for even those numbers that I tried. So that there's a potential to go, I don't know how much lower, but lower than 2.9 for sure. And this is the result, and that's the conclusion. So thank you very much for your attention.
Thanks, Mark, for the presentations. Any questions for Mark? Mark, do you have an explanation why 2 times the frequency is better than the same frequency? Because this surprises me.
I found that on papers that Valdis found, and no, I don't have the explanation. No physical explanation. Sorry, I don't. No, but I'm getting that's behavior in the mobile model. That is very simple. Getting the same with the image Valdis. So there's certainly something what's the name? Anti-resonance frequency seems to be 2x for some reason.
It seems to be a higher frequency.
It's double the frequency for some reason. I'm not an expert in vibration, but you found paper in for you stabilize a building. It's the same kind of idea that you prevent the highest amplitude due to the wind by having some compensation that is dynamic also. Yeah.
Well, very interesting.
Yeah, it's just very interesting. That's why I'm continuing, even if the university is not doing anymore, because they're looking for funding. They are not getting. They were hoping that somebody will get interested, then they will continue on their side, because they have a massive computer power, so we could investigate much faster with some funding. But right now I'm just having my own R&D for GNSIP, so that's why I'm not going fast.
Congratulations for the innovative idea that you had.
Thank you.
Any other questions for Mark?
Thank you for the presentation. Very interesting. The model, is it 1D, or does it take into account the size of the cell?
Which model you're talking? MHD Valdis or the mobile?
Yeah, the mobile.
The mobile is only the equation I showed is the full model. Up this one. This is the model. If you do the math for this, the description of this problem is a plate of aluminum attached on a wire, where the pivot is on the surface. It can oscillate this way and oscillate this way. You're providing current from the ceiling, and in between the plate, aluminum plate, and the ceiling, you have an imaginary cryolite material that is the resistivity of cryolite, but it's no friction, so it's not preventing the motion of the plate. What's preventing the motion of the plate is a friction at the pivot point, and that's the equation you get if you try to define the system mathematically. And so you solve the stability with this equation that is a fourth order complex equation, and you get the root. And that's what I'm reporting. So that's a full model is right there in front of you.
Thank you.
And you see how well it's matching the number from Emile Devan this year. It is amazingly accurate for this so simple thing. That means this mobile model captures the dynamics of the stability of the cell.
Thank you.
Any other questions? Mark?
Another one, okay.
Do you think it would be difficult for a smelter to create a variation in the compensation loop to test this?
I don't really. I was presenting previously superconductor bus bar that would be very easy to oscillate the current, and there would be no resistance to the shake. If you want to do it in a normal bus bar, I imagine that the simplest thing will be to have a battery, the same battery you use to accumulate power when the wind, and then you discharge, you charge, you discharge, you charge at that frequency.
At least for some time to do a test.
Huh? Yes, well, this is what the main purpose of this, to trigger some interest, to get ahead with the idea, if somebody believes it's worth investigating. Me, I do what I do it on my very little mean.
Thank you.
Thank you, Mark.
Thank you.